So in this question, we have actually three different logs that are set equal to each other in some weird form of an equation. So before we go ahead and continue, I always like to identify the domain of my problem. The domain of my problem is something that's more theoretical. You're not going to find this in a lot of textbooks, but I always appreciate doing it because this helps me determine whether or not my solution that I get at the very end of my computation is valid or not. So I remember with the natural log of x. So we have the natural log of x. We know that the natural log of x looks something like this. So he's going to intersect here at 0, 1. He's going to go off to infinity. But we always recognize that x must be greater than 0. So the domain of this question is that your argument must be greater than 0. If we have ln of 2, we don't have any domain issue here because this is just a constant and 2 is positive, so we know he doesn't violate the constraint of a log. Then we have ln of x plus 1. ln of x plus 1 falls in the same constraint as ln of x. We know that x plus 1 must always be greater than 0. It cannot be negative. If we solve this on the left side, we know that x must be greater than negative 1. So notice here we get two different domain constraints. So if we look and see where they overlap, that will show us something very interesting. So here we have the first guy where x is greater than 0. And then over here in red, I know that x must be greater than negative 1. X must be greater than 0, then x must be greater than 1. So the domain of this is where they overlap, which I will do in purple. So it's going to always be from 0. So it has to be the one that is the most conservative. So this is the ultimate domain of my question. If I don't get an answer that's greater than 0, then I know that I do not have a solution to this question. So again, whenever you have these issues or whenever you have logs or when you have rational expressions or radicals, always make sure to try to give yourself an idea of whether or not the solution you get can in fact be a solution. So now if I look at this, I'm going to say that I have ln of x, which is equal to ln of 2 plus ln of x plus 1. And I can go back and I can remember my log rules. I know that if I have the ln of a plus the ln of b, this equals to the ln of ab. I can multiply my arguments. So on my left side, I know that the ln of x will be equal to the ln of 2 times x plus 1. So I can go ahead and multiply this out. So this will give me the ln of x equals to the ln of 2x plus 2. So I can distribute that in. But now I know that if I have the ln of a equal to the ln of b, I know that in fact my arguments must be set equal to each other. That's the only way that my ln's can equal. Therefore here I know that x has to equal to 2x plus 2. Therefore x must equal to 2x plus 2. So I'm going to go ahead and solve this by subtracting 2x on both sides. So I get x minus 2x, which gives me negative x, which is equal to a value of positive 2. But I divide both sides by negative 1, and I get x equals to negative 2. So this is my solution I get at via my calculation. However, with logarithms, we always must go through and check our solution to make sure it's valid. So in that circumstance, if we look at this, if we were to plug it into this first guy, if we were to plug it back in to make sure it worked, we have ln of negative 2 equaling to ln of 2 plus ln of negative 2 plus 1. This guy does not exist. We cannot take the natural log of a negative number. And that also does not fall in our constraint. If we look down here, negative 2 is down here. He's not in our purple area, which we said is the domain of the problem. Therefore, since this does not fall in the domain of our problem, we know this solution does not exist. So always make sure to check your solutions to make sure they are valid. So now let's go ahead and look at this guy. So in this circumstance, this one looks very, very similar. We still are going to have the same domain issue. We're still going to have the same domain issue as we had before. We know that x must be greater than 0. And if you want to, go back and review the first couple minutes of this video to recognize how to get this domain issue. Drawing it on a number line. We know that we have 0, and he's going to be off to the right like such. So any value that falls in here is a valid solution. So now what I want to do is that I want to get my logs on one side. I want to get my natural logs on one side. So I'm going to, my plus dropped off there, I'm going to subtract ln of x plus 1 on both sides, and I'm going to subtract ln of x plus 1 on both sides. So on my left side, I have the ln of x minus the ln of x plus 1 is equal to 2. And remember, using my natural logarithm rules, my properties, if I'm subtracting two logs, I can really divide their bases. So I'm sorry, I can divide their arguments, not their bases. I can divide their arguments. So here, I can say I have the ln of x over x plus 1 is equal to a value of 2. So now I can go ahead and solve this, and I'm going to do so in a very unique way. I'm going to go ahead and I'm going to raise both sides from the e power. So I am really going to take my left side and I'm going to raise it from the e base. So I'm taking the e of the left side, I'm taking the e of the right side. And we know e to the ln will cancel, and I just get on my left side x all over x plus 1 equals to e squared. And e is just a constant. Now we're squaring him. Now in this circumstance, we can go ahead and solve for x. So I'm going to go ahead and cross multiply. So I get x equals to e squared times x plus 1. I'm going to distribute my e squared to the x and to the positive 1. So I get x equals to e squared times x plus e squared. I'm going to get my x's on the same side, so I'm going to subtract. This is the same thing. Remember, e squared times x is the same as x e squared. So I'm going to subtract x e squared. Those are the exact two same things on one side, but I'm going to do it on the other side as well. So I have x minus x e squared is equal to a value of e squared. Notice now I can factor out a value of x. So let me zoom down here. So I'm going to factor out a value x, which will give me 1 minus e squared, which is equal to a value of e squared. And notice I can divide both sides by 1 minus e squared, and I divide this side by 1 minus e squared. This cancels on my left side, and I get x equals to e squared all over 1 minus e squared. And that will be my solution. But again, we always have to check to make sure that this is a valid solution. And that's important for us to do so because we know in this circumstance that x must be greater than 0. So let's think about this. We know e, and I'll pull up this calculator here on the computer to give you an idea. So with our calculator, where is our e bus? Maybe we can get to scientific. So scientific is here. I don't see my e. No, oh, maybe it's this guy. Nope. So I'm going to have to pull out a graphing utility. So I'm going to pull out a graphing calculator. We're going to have to search here for a graphing calculator. So graphing, let's look for scientific calculator. Okay, here's our e. So if we have e squared, oops, not e, we're going to have e, where's my erase button? Here we go. We're going to have e and then raised to. We're going to use the raised to option. I think that's this right here. No, so I'm going to erase that. I'm not very good at this. I apologize. So we're going to have e raised to the second power. Notice that's going to be approximately 7.389. So e to the second power is 7.389. If we go back to this, I recognize that e squared is approximately 7.389. So x is really equal to 7.389 all over 1 minus 7.389, which will give me 7.389 all over 1 minus 7.3 is going to be negative 6.389. And this is going to be a negative number. And we know that based off of the domain of this question, that x must always be positive in this circumstance because you have this ln of x and ln of x plus 1. Since we've solved and we got our solution to be negative, we know that we do not have a solution in this equation. So in this circumstance, we will have to find the vertical and horizontal asymptotes of the following functions. So as we've discussed in a prior video, I think it was video lecture 7, we discussed the formula for determining vertical and horizontal asymptotes. So I'm just going to go ahead and find, we're going to find the vertical asymptotes. We may have to take a pause break here because the screen has has slowed down. So actually, let's go ahead and leave off here, and we'll pick it up on next video.